In the previous video, we talked about pressure, and we've learned that pressure is a force distribution over an area. And if we write the equation, we have studied that pressure is just simply force divided by the area. Now, in this lecture, we want to focus on solving this force, because sometimes you want to know, right? We want to know the magnitude of the force, and the location where it is acting. Location where it is acting. Okay, so this application is actually this can be encountered in the design of dams, for example. What else? Storage vessels, gates. Okay, this gate is a hydraulic structure, okay, etc., and other submerged, right, for submerged bodies. Okay, so what this means is that if this is our equation, then to find the force, basically we have we have to multiply the pressure times the area. Okay, so now let's draw an example of, let's say, the storage vessels. These storage vessels, let's say we have this solid boundary, and we have already learned that the pressure distribution along the y direction is a linearly varying function, right? So we have learned this already, that pressure is just simply the, or let's say the change of pressure is just equal to the weight density of the fluid times the depth, right? And now let's try to draw another storage vessels, but we want to find the pressure profile in this viewing. Let's say we have a viewing glass here, or let's say a blind flange, for example. Okay, and if we project this, this is actually a circular let's say circular window. Okay, so if we have this fluid right here, then if you want to know the pressure distribution in this geometry, then what we can find is something like this, right? Because it must be like, I mean, the pressure distribution would be something like this, but since we're only considering this area, or this bounded area, then we will be only considering this region, right? Okay, what else? Now, for example, the design of dams. Okay, so for the design of dams, the other side, I mean this side, would have a higher level of water, and then here would have a lower level of water. Okay, so for this one, since this is inclined, then we know that pressure always acts perpendicular to the solid boundary. Therefore, the pressure profile would be something like this. Okay, and then if if we convert this, if we multiply this pressure profile to the area to which it is acting, then what we get is a force, and that force is actually a resultant force, right? So Fr, this one would also be Fr, this one would also be Fr. Okay, and if we have this Fr, then sometimes you want to know where that Fr is acting. Okay, so let's say from this distance, let's say from the free surface to this Fr, right? So that's the distance we want to know. Also this one. Okay, so the question now is, why do we want to solve for the forces? Now, if you have studied already the strength of materials, okay, we want to determine the forces acting on the material, especially, let's say, here. So this one is external, right? External force with respect to this material. Okay, so we want to know the external force acting on the material so that we can properly size up the thickness of this, let's say, of this storage vessel. Okay, so now let's try to draw this in a three-dimensional view. Now let's say we have this, say, a vertical wall, then we have this free surface, right? And we'll draw this x, y, and this one would be z. Okay, and if this is the bottom, right, let's say bottom surface, then the pressure profile would be something like this, right? Okay, and this pressure profile is actually a three-dimensional, I mean, it's acting on the area, and this is the area concerned. So this is the area, and if we want to consider the resultant force, this resultant force will act at the centroid. No, actually it's not the centroid. I'm sorry to say that. That should be the center of pressure. Okay, so it's different from the centroid of the shaded area. Okay, now the question is, how do we solve for this force, this magnitude of the force, and how do we find its location? So here we'll develop a generalized derivations for the forces and the locations. Okay, so now let's consider a submerged body that is inclined or tilted at a position. Okay, so we are now looking at a two-dimensional view. And let's just say this is x, and then this is y, and then this is our submerged body. Okay, so this body could be, let's say, an arbitrary body, or you can just think of any surface, any geometry. All right, so we have learned from the hydrostatic equation that the pressure profile would look something like this. Right, so this is the pressure, and let's label this as the free surface. Okay, so if this is our submerged body, then since it is an area, then it will have a centroid, something like a geometric center. Right? So let's say this is our centroid, and now the distance from the free surface to the centroid. Okay, so the distance from the free surface to the centroid is what we call, or is what we label as h bar. Okay, so let's write it here. H bar is the vertical distance from the centroid, or let's say from the fluid surface, surface to the centroid, or this should be free surface, right? Or we can just say free surface. Okay. So referring to this surface that's exposed to the atmospheric pressure. Okay, so that's our H, and therefore to solve for the pressure is just simply the hydrostatic equation, which is just the unit weight times the, right, so times the times the h bar. Okay, so take note that this is h bar. Okay, so now let's define another parameter, the distance from the centroid to this extended, or let's say projected distance up to the free surface. So again, from this point to the centroid, that's what we call as y sub, or y bar, right? So that's the inclined distance, right? So y bar is the inclined distance from the free surface to the centroid. Okay, and the relationship of this h bar to y sub bar, or I mean y bar, since this is tilted, then we know that this has an angle. Okay, and therefore, since we have this angle, the inclined distance and then the vertical distance, then we can actually have a relationship. It's a trigonometric relationship. Okay, and now if we can write now as h bar is just simply y bar times sine theta. Okay, h bar is equal to y bar times sine theta. Okay, so now let's take a look at this force distribution. We see that that there's much force on this lower part rather than compared to this upper portion of the submerged body, right? Because as you can see, we have much larger pressure over here as compared to this one. Okay, so therefore the resultant force would be acting on this portion, portion greater than this y bar. Okay, so now let's draw the resultant force. Let's say this is the resultant force, F sub r. Okay, so the F sub r is acting at some point that's greater than this centroid. In terms of length, it's greater than the centroid. Okay, so this distance from this, this point, this is referred to as the center of pressure. So CP is simply the center of pressure where the resultant force is acting. Okay, so that's our center of pressure. It's different from the centroid. Okay, so let's just write C here. So C is just simply the centroid of the submerged body. Okay, when we see centroids, it's just like the geometric center. Okay, so this is CP, the center of pressure, and the distance from the center of pressure to the free water surface, I mean the inclined distance, this is what we call as the YCP, Y sub CP. Okay, so Y sub CP is just simply the inclined distance from free surface to the center of pressure. Okay, so this distance, this Y sub CP, can be calculated using this equation, right? Y bar, which is simply the distance to the centroid, plus I, the moment of inertia, divided by Y bar times the A. Okay, so this one is the moment of inertia, and we can solve for this, or we can use tables. Okay, so this can be found, for regular shapes, the equation for the moment of inertia can be obtained easily. This one is the centroid, right? So centroid, or the inclined distance, that's right, inclined distance to the centroid. Then this one is the area. Okay, and when we say area, we are referring to the submerged area. Okay, so as if you can see that this Y bar, right? So this is it. This is the Y bar plus this term right here, and this term is sometimes referred to as the eccentricity. So how far is it from the centroid? Okay, and this will be our eccentricity. How far is it? And it's given by this mathematical expression. Okay, so that's our working equation, this one and this one as well. Okay, and what else? Now sometimes you are asked to find this x sub CP, which is just simply the x distance to the center of pressure. That's x bar plus IXY all over A times Y bar. Okay, you might notice this one. This is XY, meaning that this is a product of inertia, which is different from this I right here. Okay, later on we will discuss in more details regarding this area and then the moment of inertia and other things. Okay, so this one is the product of inertia, and this one should be, I think this one should be x bar, I guess, because we're solving for x. Let's have to check. This one should be y bar, sorry. Right, so this should be A times Y bar. Okay, so that's the derived equation. Okay, so now let's review some concepts on the centroids, the area, and then the moment of inertia. Okay, so let's just, let's start with the centroids. Okay, so centroids basically what what it's like, or what it is something like the geometric center. Okay, so for example, um, we have a square or rectangle. Then what is the geometric center? Now let's say we have this base over here. The distance here is b, and then the height here is h. Now if we want to find the position of the center, then that's gonna be b over 2, right? And then this one would be h over 2. Now for a circle, then of course, if this is our circle, then we have a radius. Let's say we have this radius, and of course the center is just equal to the radius. Okay, and then for a triangular shape, we have here the center is somewhere in this position, or in this location, and the distance from this centroid to I mean, with respect to the base, that's gonna be let's say this is our base, so it's just b over 2. This will be b over 2, and if that is where base is, let's say designated as b, then if this is our height, then the distance from this line to the centroid, that is h over 3, that is 1/3, and then this one is h, that would be 2/3 times the h, right? And then the unit of this for the centroid is just simply in meters, right? That's the geometric center. So that geometric center could be with respect to x, right? That can be with respect to x, right? X, or with respect to y. Okay, so it's just a position, and the area is just basically the product of the length. So length, the x, let's say, and then times the length along the y. Now for the square, the area is just simply base times height, right? So this is our area. And for this one, the area of the circle is just in terms of r, that's just pi r squared, or in terms of the diameter, that's just pi d squared all over 4. Okay, and then for this one, this is just 1/2 base times height. Okay, so it's just the rectangular portion. All right, so, and then you just divide that by 2. All right, so now let's move on to the moment of inertia. Okay, so recall that in statics we have already studied that the moment of inertia is basically something like the geometric resistance to bending. Okay, so for example, we have this cross-sectional we have this cross-section, or we have this geometry, the same geometry, except that the one is oriented in this position while the other one is oriented in this position. Okay, so let's say they have the same cross-sectional area, they have the same dimensions, the base and the height, they're exactly the same, except that the difference is with respect to the orientation. Now we'll try to rotate this one to bend. Okay, and then this will be our, let's say, axis of rotation. Axis of rotation. So we have actually, let's say we write XX, and then this one is YY. So it means that if we rotate this along the X direction, then you would notice that it is much more easier to bend this this position than this one, right? Okay, so for example, you have a ruler. Okay, so this one, for example, so if you have this position, then it is much easier to bend than this one. Okay, so let's draw the force, right? This one. Okay, so the question is, why is that? Why is it much harder to bend this orientation compared to this one? And the answer is because there's a lot, there's more area, right? There's more area away from the axis of rotation. Okay, so that's the reason why. Okay, so this one, this moment of inertia, they can be found on equations can be found on tables. Okay, so tables, let's say from textbooks, there are a lot of equations for regular shapes. Okay, so for this one, let's say for square or rectangle, the moment of inertia, if we if the rotation is along the x-axis, okay, so meaning if this is our axis of rotation, then the equation would be base times height, okay, cube divided by 12. And then for the circle, we have, okay, IXX, which is just the same as the if you rotate it along the y-axis. Okay, so the answer, the explanation is that because they're just symmetrical in whatever axis. Okay, so this one is pi d to the fourth all over 64, or you can also convert that to radius if you'd like. And this one is base times height cube all over 36. Okay, so this is our equations, typical equations for this type of shapes. Now for other irregular shapes, like for example an ellipse, then you can just refer to the tables, or if it's in the exam, then I can just give you the equation for the moment of inertia. Okay, so now let's check the units of the moment of inertia, which is, this one is in length, so meter, then meter cube, which means that the unit is meter to the fourth. Okay, so I guess that's our fundamentals, and in the next videos we will start solving problems regarding these static these forces on submerged bodies. Okay, so see you in the next video.